Hi everyone, in today's video we're going to go over electrocyclic reactions, a new class of reactions in this course. It is my goal that by the end of this video you would be able to draw and identify the products of electrocyclic reactions, and we're really thinking about this reaction in both directions, which is the cyclization part and the ring opening part. You'll be able to draw curved arrow mechanisms as well as transition state structures for these electrocyclic reactions. And then lastly, we're going to end with using molecular orbital theory to explain the observed stereochemical outcomes of electrocyclic reactions. So electrocyclic reactions can be defined as the cyclization of conjugated polyenes. Formally, we think about this as the conversion of one pi bond in the reactant side to a sigma bond in the product side. As an example, I'm going to show you, so here is a hexatriene with 3 pi bonds. And in this particular cyclization reaction, we see that the product side, we have lost one of the pi bonds, and we have formed a sigma bond, where I've highlighted in red. The curved arrow mechanism looks like how I've shown you here, where you can imagine a cyclic flow of electrons where the pi bond between 1 and 2 breaks and forms a sigma bond between 1 and 6. And then 5 and 6 pi bond breaks, moves over to form a pi bond between 4 and 5. And then the same thing happens between 3 and 4 and 2 and 3. When we're thinking about the transition state for this particular reaction, you can imagine a cyclic flow of electron density where now essentially you could draw out dotted lines that connect every single carbons 1, 2, 3, 4, 5, and 6 in a cycle. And this is, as we know, representative transition state structure for all pericyclic reactions. You should expect that a flow of electrons should be occurring between them. So now let's consider the stereochemistry of electrocyclic reactions. And we can best do this with an experimental observation. So consider this substrate. This is our 2E 4Z 6E 246 octatriene. And this particular substrate undergoes electrocyclic reaction in heat to form, in this particular case, a cis disubstituted cyclohexadiene. On the other hand, consider the diastereomer of A, and this is our 2E 4Z 6Z 246 octatriene. When this particular substrate undergoes electrocyclic cyclization, its products are actually now your trans disubstituted products. So what we are observing here is a clear stereospecificity where the stereochemistry of our reactant is actually dictating the stereochemical outcomes of our products. And so we need to understand what is this origin of selectivity. And it turns out that molecular orbital theory can be used to explain the stereoselectivity of electrocyclic reactions. So if we take just one of those substrates that we just looked at as an example, and we consider its stereochemical outcome, looking really closely at our reactant, what we could notice is that the pi bonds between 6 and 7 and 2 and 3 has actually been broken, and that's key. And it's from those broken bonds that we get the sigma bond that is formed between carbons 2 and 7. And so when you're thinking about how these bonding would work from a molecular orbital perspective, we have to assume that the carbon 2 carbon 7 sigma bond that was formed must have been made from the p orbitals that we started with in carbons 2 and 7, and it must have come from a sigma overlap of those p orbitals. So Now we are going to delve more deeply into how to understand and predict the stereochemical outcomes of these electrocyclic reactions. And we're going to keep the same example. And the key thing to note here when you're talking about the origins of stereoselectivity is you really need to think about the HOMO orbital and how the HOMO orbital, which is our highest energy occupied molecular orbital, how that has to twist in order to achieve that sigma overlap that we want between carbon 2's p orbital and carbon 7's p orbital. And so a lot of this really requires us to remember how to build our molecular orbital diagram for conjugated pi systems. And so we see in this particular molecule, this substrate that we start with has 6 p orbitals that are being used to form pi molecular orbitals. And there are 6 pi electrons that exist within the pi molecular orbital system. Lastly, given that the reaction is going through heat, this reaction is under thermal conditions, and that's going to tell us where that HOMO orbital is going to look like. We have covered drawing pi molecular orbitals in previous classes, so I'm just going to show you what the HOMO orbital looks like in this particular case. And recall that because we have 6 pi electrons, we are going to fill up our pi molecular orbitals in such a way that we should only expect 2 nodes within our 6 pi electron system. So what I'm drawing for you right now, we see our first node in between carbons 3 and carbons 4. And then there will be a second node that will arise between carbons 5 and carbon 6. And so that would then complete our molecular orbital picture for the 6 pi electron system. So please note, the key thing here is the symmetry at the ends of the pi molecular orbital for the HOMO. Note in this particular case, the lobes at the very ends of the HOMO orbitals are in the same phase. So they're on the same side. So you can have your yellow phase is on the same side as each other, and the purple phase is on the same side as each other. This particular arrangement is going to dictate how the p orbitals are going to twist in order to form sigma orbitals. So now let's look at an example and where we're going to strip out the rest of the molecule and focus on the ends of the p orbitals that are associated with your pi molecular orbital system. So take note of how we have oriented the molecule with A, B, C, and D, and also take note of the symmetry of the pi molecular orbital. In this particular case, we have the two ends in the same phase, so we have a symmetrical pi molecular orbital. In order for these two lobes to orient themselves to achieve sigma overlap, we are going to need to rotate one of the lobes in a clockwise direction while the other one is in an anti-clockwise direction or counterclockwise direction. And there are two possible ways you could have rotated. So we have rotation 1 or rotation 2. Now, depending on how you rotate, let's say we do the rotation 1, you can imagine that if you rotate the carbon containing A and B in a counterclockwise direction, B will now be oriented up and A will be oriented down, as well as if you rotate the carbon with C and D in a clockwise direction, C will be up and D will be down. And we note that in this particular scenario, you will have your sigma overlap between the purple lobes of the p orbitals on both carbons. The other orientation is actually precisely the same idea. It's just that we're rotating clockwise for the carbon on the left and counterclockwise for the carbon on the right. And in this scenario, the yellow lobes would then orient in such a way that you can then have an effective sigma overlap. And because the two lobes have to be rotated in an opposite direction, we call this a disrotatory motion. And this is what's going to dictate the stereochemical outcomes of this reaction, where in this case, regardless of which rotation 1 or 2 you use, A and D substituents are going to be on the same side of that ring, and B and C, those are going to be on the same side of the ring as well. So that is a stereochemical outcome for this particular reaction. So now, in contrast, imagine a conjugated polyene, and this time still the same substituents A, B, C, and D. But in this case, consider the HOMO orbital being anti-symmetric, meaning that the ends of the lobes have opposite phases. So thinking about how these two orbitals are going to have to twist in order to form a sigma overlap, we would imagine that both orbitals have to rotate in the same direction, whether both clockwise or both counterclockwise, in order to actually achieve a sigma overlap. As a result, we call this a conrotatory rotation. And so now let's think about what this would look like when we do this conrotatory rotation. In this case, B will be on top and A will be below on the carbon on the left. And the carbon on the right, you would have D on top and C below. And if you do this, the purple lobes of the p orbitals of both carbons are going to overlap in a sigma fashion to form a sigma overlap. In our second rotation, here now A will be on top and B will be below on the carbon on the left. And then on the carbon on the right, you would have C being on top and D being below. And then this rotation would result in the yellow lobes or overlapping in a sigma fashion. In this case, the stereochemical outcomes are now pretty clear. We should expect that B and D will end up on the same side of the ring in your product, and A and C will end up on the same side, which is actually opposite from the case where we saw in the previous example, because now we are dealing with an anti-symmetric molecular orbital. So you can kind of think about this as a summary. If you have a symmetrical orbital, you should as your HOMO, you should expect a disrotatory motion or rotation, meaning that those two orbitals are going to rotate in opposite directions to form a sigma overlap in your electrocyclic reaction. And if you have an anti-symmetric orbital, which means that those p orbitals are in opposite phases, then you should expect a conrotatory motion, meaning that both orbitals should rotate or twist in the same direction to achieve your sigma overlap. If you know these two things, that would help you predict or start to predict the stereochemical outcomes of electrocyclic reactions in this class. So now let's revisit the example where we had our 2E4Z6E octatriene undergoing electrocyclic cyclization. And in order to understand how to predict this particular chemical reaction, we need to remember or know how to identify the number of pi molecular orbitals that exist within this particular pi molecular system. So we need to know that the pi MOs come from 6 p orbitals, which means that we will have 6 pi molecular orbitals to fill. We need to know that there are 6 pi electrons in this pi molecular network, and as well we need to know that we are under thermal conditions, which is the heat that is denoted on top of the arrow. And that is telling us that we are under relaxed electronic configuration, which means that we would fill up our electrons as usual with no excitations. Knowing this, we have to then be able to build up our 6 pi molecular orbital system and know that our HOMO orbital is going to be psi3. Psi3 will be our symmetrical pi molecular orbital with 2 nodes. So we have done this in the previous video, so I'm not going to repeat this here. But now, once we know that it's a symmetrical pi molecular orbital, we can build up this cartoon diagram, which just shows the p orbitals at the ends of the pi molecular orbital picture. So that's the p orbitals on carbons 2 and 7. We're also denoting where our CH3 groups, 1 and 8, are on this particular picture. And as we're seeing, the way we are showing those CH3 groups, 1 and 8 should be facing away from each other, just like how we are seeing in our actual substrate above. And under these conditions, we would expect that we should assume disrotatory motion to twist the two p orbitals so we can achieve our sigma overlap. And there are two different ways we can think about the disrotatory motion. So you can imagine both 8 and 1 being on top, or 8 and 1 being below. And depending on which one you do, you would either have the yellow lobes on the p orbitals overlapping in a sigma fashion, or you have the purple lobes overlapping in a sigma fashion. But note that if you look at these two pictures, these are actually the exact same compounds. All right, so now that we've figured it out, we now know that our product needs to have the two CH3 groups on the same side of our cyclized product. Then we can now draw our cyclization, but I guess to remind you, we can draw a curved arrow mechanism where the pi bond breaks between 2 and 3. We form a sigma bond between 2 and 7, and then we move the other two pi bonds 1 over. And if we do this, we will form a six-membered ring with pi bonds on 3 and 4 and 5 and 6. And now our substituents, our CH3 groups on carbons 2 and 7, are going to be on the same side. We can draw them both wedged, which is another way of saying it's up, if you will, or we can draw them both dashed. Either way, it's going to be the exact same molecule. And so therefore, that would be our one product of this particular electrocyclic cyclization, where you can, in this case, I just drew it as both being wedged and going up. Okay, so this is how we can actually predict the stereochemical outcomes of electrocyclic cyclizations. You kind of have to do this in your head, or at least on a piece of paper, where you go to the molecular orbital picture. We see what the symmetry of the pi molecular orbital is, and that will help dictate how the molecule is going to twist in order to achieve that cyclization. Okay, so now what I want you to do is take what we have just covered, looking at the stereochemical outcomes of a reaction. And now I wanted to use the same molecular orbital theory to explain the stereochemical outcome of this reaction. It's also an electrocyclic reaction, but note that I have slightly changed the stereochemistry of the reactant. And we want to do is to figure out why we form this particular stereochemical outcome of our product. All right, so now we're going to revisit this octatriene substrate that we have already worked through. And we've already established that under heat, the product you get is the cis disubstituted cyclohexadiene. However, if you take this particular substrate and you do the same electrocyclic cyclization, this time under light, it turns out the trans disubstituted cyclohexadienes would then become the major product. And so recalling from our previous course classes, we've seen that essentially what we're doing is we're switching up the conditions, whether it's thermal or photochemical, in which we're taking part in this reaction. And so the real question here is, why does the stereochemical outcome change when we go from thermal to photochemical conditions? And recall that we have talked about this, that when you go from a photochemical conditions, you are essentially exciting your electrons from the pi to the pi star, also known as the pi to pi star transition, which then takes your HOMO into a new level that has a new type of symmetry. And so we're going to look at this, how the symmetry of the HOMO changes and how that would then dictate the stereochemical outcomes of your electrocyclic cyclization. And so what we really need to think about is what is the symmetry of the HOMO orbital, whether you're in the relaxed case, whether there's the heat under thermal conditions, or the excited state, which is under photochemical conditions. We have done this before, so I'm going to really just focus on getting you to the correct answer. So now let's draw out the HOMO orbital for the situation where we're under thermal conditions. We've already covered this before, right? This is your Psi 3 orbital when you're having a 6 pi molecular orbital system. It is symmetric with two nodes. And so what I am drawing here essentially is that symmetrical HOMO orbital under a relaxed electronic configuration with 6 pi electrons in a 6 pi molecular orbital system. Under photochemical conditions, however, we are now one orbital above. So we're at Psi 4. And Psi 4 is anti-symmetric. Remember that as you go up a level, you go from symmetric to anti-symmetric and back to symmetric again. The anti-symmetric orbital has three nodes, and that's what we're seeing here between 2 and 3, between 4 and 5, and between 6 and 7. But note the symmetry of the ends of our pi molecular orbital and how that's going to dictate what's going to happen with the rotation. So under thermal conditions, those two lobes are in the same phase at the very ends, 2 and 7. And so in order to form a sigma overlap, we expect to undergo a disrotatory rotation such that 1 and 8, those CH3 groups, will end up on the same side of that disubstituted ring, or cis, which is what we're seeing above in the products. Under photochemical conditions, however, those two lobes are now in opposite phases. And so now, in order to engage in a sigma overlap, we must go through a conrotatory rotation. And in that case, if you imagine this rotation, 1 and 8 would end up on opposite sides of the disubstituted cyclohexadiene, and then you would form two different stereochemical outcomes in that particular case. And so that is how you can use the symmetry of the HOMO orbitals to really dictate to understand the stereochemical outcomes. Keeping in mind that thermal and photochemical conditions essentially flips the symmetry. So whatever it was in the thermal conditions, if it was symmetrical, it will be anti-symmetric in the under photochemical conditions and vice versa. So lastly, I would like you to practice some problems that are going to extend your understanding of pericyclic reactions a little bit. So these are still to predict the product questions. You're going to try to figure out what the products are, including stereochemical outcomes. In this first one, the first scenario, we're actually going to go back. So instead of going to a cyclization product, we're going to open up the ring. And so here we have our disubstituted cyclohexadiene, and we want to do a retrocyclization in light. And so just note that it's still a pericyclic mechanism, so you can draw those curved arrow mechanisms similarly. Just make sure you move the arrows around in the ring. Also, make sure that you can sort of, when you're tracing the curved arrows, you know which bonds are forming and which bonds are breaking. So this is really important because you need to be able to predict the constitution of your product in this reaction. You also want to think about the symmetry of the HOMO orbital when the ring opens up. So when the ring opens up, it will end up becoming a 6 pi electron system. So you want to think about what that symmetry looks like. And that's going to help you to understand how the substituents are going to twist in order to form the product. So try that out. In this second example, we are dealing with a different polyene with a different length. So now we're dealing with a 4 pi electron system with 4 pi molecular orbitals. So you kind of need to be able to know how to determine the number of pi molecular orbitals and number of pi electrons are in the system. But once you've done that, you can do the same thing we've done in this video. So you determine the symmetry of the HOMO orbital, and then you start to rotate or twist, and you want to monitor what's going on with the methyl groups as you rotate to actually get that sigma overlap to occur accurately. And so with that, I hope that by the end of this video, you're able to start thinking about the product of electrocyclic reactions. We focus on cyclization, but certainly the ring opening is still one you can certainly do. You want to be able to draw curved arrow mechanisms and transition state structures of these electrocyclic reactions, which we've covered, and we've certainly covered in detail how to explain the stereochemical outcomes of these reactions using the symmetry of your HOMO orbitals and molecular orbital theory. Thank you so much for watching this video, and I will see you in class.